Imagine a vehicle operating as a digital nervous system. It scans the pavement while simultaneously talking to every sensor in its vicinity, reacting to a hazard before it enters a human's field of vision. This communication framework is called V2X, or Vehicle to Everything. It provides the data backbone required for both advanced driver assistance and fully autonomous navigation. The V2X ecosystem functions through four primary communication pathways. Local pathways include vehicle-to-vehicle, which allows cars to share braking status to avoid collisions, and vehicle-to-infrastructure, which syncs the car with traffic signals to optimize timing. External pathways connect the car to the wider world. Vehicle-to-pedestrian alerts the car to nearby smartphones or wearables, while vehicle-to-network links the car to cloud telematics and remote servers. The safety data is compelling. The NHTSA estimates that a nationwide V2X system could prevent 439,000 crashes every year. In Georgia's Fulton County, a pilot program using connected school buses saw travel times drop by 13% through signal synchronization. Despite these results, widespread deployment has stalled. The rollout is currently blocked by an invisible technological barrier. A decade-long standards war is the primary friction holding back smart cities. Two competing protocols are fighting for dominance: DSRC and CV2X. These protocols function as two incompatible digital languages. Automakers and city planners are forced to bet millions of dollars on one specific winner before laying down a single mile of hardware. Early adopters placed bets on the legacy standard. Certain early models, like this Cadillac, were manufactured with DSRC hardware already integrated into their communication systems. More recently, other manufacturers shifted course towards cellular-based technology. This Volkswagen Golf was the first passenger car to use the newer CV2X protocol. Choosing the wrong standard today strands millions of dollars in hardware and leaves vehicles speaking a language the rest of the city can't understand. To see which path is viable, we have to look at the engineering inside both options. DSRC stands for Dedicated Short-Range Communications. It is a mature technology based on the IEEE 802.11p standard, essentially a specialized version of Wi-Fi hardened for use in fast-moving cars. It operates on the 5.9 GHz band to create decentralized ad hoc networks between vehicles. It functions independently, requiring no connection to external cellular towers. The primary engineering advantage here is ultra-low latency. Because the data stays local, it is suited for instant safety alerts, like a warning that the car immediately ahead has slammed on its brakes. However, DSRC lacks wide area network capabilities, or V2N. This missing link prevents the car from handling cloud-based fleet management, remote diagnostics, or over-the-air software updates through the same hardware. Its range is also limited to short distances and a direct line of sight. The system cannot see a traffic hazard 3 miles down the highway. DSRC is a highly effective tool for localized safety, but it cannot connect the vehicle to the broader digital economy. CV2X is the challenger, built on 3GPP cellular standards that utilize LTE and 5G networks. CV2X's advantage is a unified hardware solution operating in dual modes. The PC5 interface handles direct car-to-car communication without cell towers, matching DSRC safety. Simultaneously, the UU interface connects to the cellular network, enabling long-range telematics, traffic routing, and real-time mapping updates. This versatility comes with a trade-off in complexity. CV2X requires more intricate chipset architectures and ties the vehicle's network features to the reliability of commercial telecom carriers. Unlocking its full potential also requires massive infrastructure investment. Cellular telecom carriers must build out 5G networks specifically to support the ultra-low latency needed for autonomous driving. CV2X bridges the gap between direct local sensors and cloud-based data, but it ties a car's intelligence to the strength of a cellular signal. Running DSRC and CV2X at the same time creates a dangerous fragmentation. They act as two incompatible digital languages used on the same roads. If a DSRC car broadcasts a crash alert, a newer CV2X car is completely blind to the warning, leading directly to near misses and dangerous collisions. The market was unable to resolve this incompatibility. To ensure public safety, federal regulators had to intervene and select a single winner. The turning point arrived when the U.S. Federal Communications Commission reallocated the radio spectrum. Citing the failure of DSRC to reach a critical mass, the FCC stripped spectrum rights away from the old standard, reallocating those frequencies exclusively to V2X and Wi-Fi. This ruling effectively ended DSRC's future in the United States. It forced planners to abandon legacy hardware and begin the transition to cellular technology. The technical debate is over. DSRC was the right technology for the isolated networks of 2010, but V2X is the mandatory foundation for the 2020s. V2X won by routing local safety and wide area cloud data through a single cellular architecture. We are currently migrating from old DSRC units to baseline LTE V2X networks. The final step is upgrading to 5G, providing the ultra-low latency required for real-time sensor sharing. V2X is the global victor. All industry players must now pivot their capital strategies to align with this cellular reality. For city infrastructure planners, the mandate is immediate. Stop capital expenditure on legacy DSRC roadside units. Align all upcoming smart intersection projects with 3GPP Release 14 and 15 standards to ensure your investments are compatible with modern vehicle fleets. For automotive engineers, hardware must be designed with long-term interoperability in mind. Prioritize dual-mode chipsets that can handle both the PC5 direct interface and the UU network interface. This future-proofs the vehicle against varying regional deployment timelines. For tech enthusiasts and consumers, the timeline for this transformation is measured in decades, not years. Widespread integration requires a massive overhaul of telecom infrastructure and the billions of legacy vehicles already on the road. A zero-crash future is years away, but the industry has stopped arguing over which language to speak and is finally ready to start building.